Welcome to another deep dive. Today, we're digging into, well, literally, digging into the ground beneath our feet to talk about sedimentary rocks. Now, you might think rocks are just, rocks, boring, but these aren't just any old rocks. They're more like Earth's ancient diaries.
That's a great way to put it. Pages filled with the planet's history.
Exactly. They tell us about climates from millions of years ago, maybe helping us understand future ones. They hold the resources that power our world.
Right. If you think of igneous and metamorphic rocks as the Earth's crust's deep bones, sedimentary rocks are like the skin. They're at that dynamic interface where rock meets water, air, and life. And for you, trying to get a handle on this stuff quickly, understanding them is kind of a shortcut to Earth's big secrets.
So what's the plan for today? We're basically going to follow a tiny grain of sand or maybe some dissolved ions on their journey, from breaking off an old rock, traveling, settling down, and finally becoming part of a new sedimentary rock. We'll look at the different types, where they form.
The clues they hold.
Yeah.
Our
Yeah.
mission is to guide you through that whole process and show how these rocks link up with really vital global cycles, like the carbon cycle. Super important.
Okay, let's unpack this.
Let's do it.
So, starting right at the beginning, sedimentary rocks form at the Earth's surface, part of the big rock cycle. What kicks the whole thing off?
It all starts with weathering. Think of it like Earth's demolition crew. Existing rocks could be igneous, metamorphic, even older sedimentary ones get broken down. Physically disintegrated, like frost shattering things apart, or chemically altered, like acid rain dissolving minerals. This makes the raw materials. Solid bits and pieces and dissolved stuff, ions.
Okay, so weathering creates the raw stuff, but it doesn't just sit there, right? Gravity, water, wind, ice, they get involved.
Precisely. Those are the agents of erosion and transport. They pick up the weathered debris and move it, often breaking it down even more as it tumbles along, until eventually it gets deposited somewhere else, maybe a river mouth, a lake bottom, the ocean floor. And that loose material, that's what we call sediment.
And then comes the transformation, turning that loose sand or mud into solid rock. That's lithification, you said, literally stone making.
Yeah.
Why is this so important? I mean, besides just making more rocks.
Oh, they're incredibly important for a few big reasons. First, coverage. They blanket about 75% of the continents and pretty much the entire ocean floor. So they form this amazing layered record of what Earth's surface was like in the past.
Yeah.
We study their textures, what they're made of, the structures like layers.
And fossils, can't forget fossils.
Absolutely. Fossils are key. All this lets geologists reconstruct ancient climates, vanished ecosystems, even where the continents used to be. It's like reading Earth's autobiography page by page.
And that ancient history has real-world consequences for us today, doesn't it? It's not just academic.
Not at all. Think about energy. Coal, oil, natural gas, even uranium. Major energy sources are found in sedimentary rocks. That's huge. Plus, things like iron, aluminum, manganese, phosphate for fertilizers, materials for cement, gravel for construction. It mostly comes from sedimentary deposits.
Wow, okay. And groundwater, too.
And groundwater, yes. They're the main reservoirs we tap for drinking water and agriculture. So, understanding these rocks is fundamental to managing resources and, frankly, our future.
Okay, so sediment gets deposited, then lithified. But you mentioned different origins. What are the main sort of families or categories of sedimentary rocks we need to know?
We usually group them into three main types based on how they form. First, detrital sedimentary rocks made from solid particles like sand or mud. Second, chemical sedimentary rocks. These form when dissolved minerals precipitate out of water, kind of like salt forming when water evaporates. And third, organic sedimentary rocks, which are made from the accumulated remains of organisms. Coal's the classic example there.
Got it. Detrital, chemical, organic. Let's start with detrital, the ones made from solid bits. What are the main ingredients we find in those?
The most common components are usually clay minerals. They're the tiny, flaky products you get when rocks like granite chemically weather and quartz. Quartz is super tough, really resistant to breaking down further. So it tends to survive long journeys. If you find lots of less stable minerals like feldspar or mica, it often suggests the sediment wasn't transported very far or very fast. It didn't have time to decompose completely.
And how do we tell these detrital rocks apart? You mentioned particle size earlier.
Yeah, particle size is the number one thing. It tells you so much about the energy of the environment where the sediment was deposited. Think about it. A fast, turbulent river can move big pebbles, right? But a slow, quiet lake, only the tiniest mud particles can settle out there. So grain size is a direct clue to the past environment.
Okay, makes sense. Let's look at some examples then, starting small. What forms in those quiet environments?
That would be shale. It's actually the most common sedimentary rock overall. Made of silt and clay-sized particles, really, really fine stuff. You find it forming in very low energy settings, lake bottoms, river floodplains, lagoons, deep ocean basins, places where the water is calm enough for these tiny particles to settle out.
And shale often splits into thin layers. What's that called again?
Facility. Yeah, it splits easily into thin sheets. That reflects the original layering of the fine mud settling out. If you picture the Grand Canyon, shale often forms those gentler slopes between the big, blocky cliffs made of sandstone or limestone.
Right. And you mentioned black shale earlier, telling us about oxygen. How does that work?
Yeah, that's fascinating. If shale is black, it usually means there's a lot of organic matter preserved in it. That happens when the sediment accumulates in water that's poor in oxygen, like a swamp or a stagnant basin. Without oxygen, the organic stuff doesn't fully decay. So black shale is like a snapshot of an ancient, oxygen-starved environment.
Cool. Okay, moving up in size. Sandstone. Made of sand, obviously. What clues can we get from sandstone besides just it used to be sand?
Oh, sandstone is packed with information. You look at a few key things. First, sorting. Are the grains all about the same size, or is it a mix? Well-sorted sand-uniform grains often means it was transported by wind, like in sand dunes. Think of the massive Navajo sandstone in Zion National Park, or maybe waves on a beach constantly washing it.
Okay, so well sorted means steady transport, like wind or waves. What about poorly sorted?
Poorly sorted sand, a jumble of different sizes, usually points to rapid deposition. Maybe a flash flood or sediment dumped quickly near its source, like from a melting glacier or a fast mountain stream. Not much time to sort things out.
And the shape of the grains matters too. Round versus angular.
Exactly. Rounded grains suggest they've traveled a long way, tumbling and getting their sharp edges knocked off, like river pebbles. Angular grains tell you the sediment is immature. It hasn't traveled far from where the original rock broke down, maybe deposited right at the base of a cliff.
What about what the sand is actually made of?
Right, mineral composition. If it's mostly quartz sandstone, that indicates a lot of weathering and transport, because only the toughest minerals survived. But if you see a sandstone with, say, 25% or more pinkish feldspar grains, that's called arkose, and suggests it came from eroding granite nearby, probably in a drier climate where chemical weathering wasn't as intense.
And there was one more. Gray something.
Graywacke. Yeah, that's a dark-colored, typically poorly sorted sandstone with lots of quartz, feldspar, but also little fragments of other rocks and clay mixed in. It often forms from turbidity currents.
Turbidity currents? What are those?
Think of them as underwater landslides or avalanches of sediment. They rush down the continental slope into the deep ocean, depositing sediment very quickly. Graywacke is often associated with those rapid deep water events.
Okay, interesting. So from shale to sandstone.
Oh,
What about the really big pieces, gravel-sized stuff?
that brings us to conglomerate and breccia. Both are made of particles larger than 2 millimeters gravel size. The difference is in the shape of that gravel.
Let me guess. Rounded versus angular again?
You got it. Conglomerate has rounded gravel class. Tells you the gravel was transported by high-energy water, like a powerful river or crashing waves that rounded the edges. Breccia, on the other hand, has angular, sharp-edged fragments. This means the material was deposited very close to its source. It didn't travel far enough to get rounded. Think of landslide debris or fault zones where rock gets shattered.
Okay, so that covers the detrital rocks formed from physical bits. Now, what about chemical sedimentary rocks? These form from dissolved stuff precipitating out.
Exactly. Ions dissolved in water, maybe seawater, lake water, groundwater, come together to form solid minerals. This can happen through purely inorganic processes like evaporation concentrated the ions.
Or living things can be involved.
Or through biochemical processes, yes. Organisms pull dissolved substances out of the water to build their shells or skeletons. When they die, these hard parts accumulate and can become rock.
And the most common chemical rock is, you mentioned it forms reefs.
Limestone. Yep. Makes up about 10% of all sedimentary rocks. It's primarily made of the mineral calcite, which is calcium carbonate, KCO3. And most limestone does have a marine biochemical origin. Corals are a great example, building massive reef structures. Australia's Great Barrier Reef is a modern example, but we find huge ancient reef systems preserved in the rock record, like in the Guadalupe Mountains in Texas. Life literally building mountains.
That's incredible. Are there other kinds of limestone made by organisms?
Oh, absolutely. There's coquina, which is basically a rock made of loosely cemented shell fragments, looks like a beach shell hash turned to stone. And chalk, like the White Cliffs of Dover. That's a soft, fine-grained limestone made almost entirely of the microscopic calcite skeletons of marine plankton.
Wow. And what about limestone formed without life directly involved? Inorganic limestone.
Yes, that happens too. Travertine is a type you often see in caves forming stalactites and stalagmites as water drips and releases CO2, causing calcite to precipitate, or around hot springs. And there's oolitic limestone. This one's cool. It's made of tiny spheres called oids. They form in warm, shallow, agitated marine water as layers of calcite precipitate around a tiny nucleus like a sand grain, rolling back and forth. Little rock pearls, basically.
Rock pearls, love it. Okay, besides limestone, what other chemical rocks are important?
Well, there's dolostone. It looks similar to limestone, but the main mineral is dolomite, which is a calcium magnesium carbonate. Its exact origin is still a bit debated, but it often seems to form when magnesium-rich water alters existing limestone. Then there's chert. This is a very hard, dense rock made of microcrystalline quartz, silica SiO2. It can form in a few ways, sometimes from accumulating silica-rich skeletons of microscopic organisms like diatoms or radiolarians, or sometimes silica replacing other minerals.
Chert comes in different colors, right? Like flint.
Exactly. Flint is the dark variety, often found as nodules in limestone or chalk. Jasper is the red variety, colored by iron oxides. And petrified wood is essentially chert, where silica has replaced the original wood structure, preserving it perfectly.
And chert was super important for early humans making tools.
Absolutely. Because it's hard and fractures with a sharp-edged conchoidal fracture, it was ideal for making arrowheads, spear points, scrapers, a really vital resource.
Okay, one more type of chemical rock you mentioned involves water disappearing. Evaporates.
Evaporates, yes. These form when a body of salt water, like a restricted bay or an inland lake in an arid region, evaporates. As the water disappears, the dissolved salts become too concentrated to stay dissolved, and they precipitate out as minerals. Common examples are rock salt, which is made of the mineral halite, sodium chloride table salt, and rock gypsum, made of the mineral gypsum used to make plaster and drywall. Think of the Bonneville Salt Flats in Utah. That's a modern evaporate environment.
Got it. So, detrital, chemical, that leaves organic sedimentary rocks. Coal is the main one.
Coal is the primary example, yes. It's unique because it's composed mainly of organic matter, the compressed, altered remains of ancient plants. It forms in stages. First, you need lots of plant material accumulating in an oxygen-poor setting, like a swamp, so it doesn't completely decay. This forms peat.
Like you find in bogs today.
Exactly. Then, as the peat gets buried by more sediment, it gets compacted and heated. Shallow burial turns peat into soft, brown lignite. Deeper burial, more pressure and heat, dries off water and gases concentrated the carbon, and turns lignite into harder, black, bituminous coal. That's the most common type mined for energy.
And there's an even higher grade.
Yes. If the bituminous coal is subjected to even more heat and pressure, usually during mountain building, it metamorphoses slightly into anthracite. That's the hardest, highest carbon coal, very shiny. It's technically a metamorphic rock, but its origin is sedimentary.
Okay, so we have all these different sediments, bits of rock, precipitated minerals, plant matter. How exactly does that loose stuff turn into solid rock? You mentioned lithification, but also a broader term, diagenesis.
Right. Diagenesis is the umbrella term. It includes all the changes, chemical, physical, and biological, that happen to sediment after it's deposited, but before it gets into the realm of metamorphism, which involves much higher temperatures and pressures. Diagenesis happens mostly in the upper few kilometers of the Earth's crust. It includes things like minerals reacting with groundwater or unstable minerals recrystallizing into more stable forms, like aragonite shells often recrystallizing into the more stable calcite in limestone.
And lithification fits under that umbrella.
Yes. Lithification is the part of diagenesis that specifically turns soft sediment into solid rock. And the two main processes of lithification are compaction and cementation.
Compaction seems straightforward, just squeezing.
Pretty much.
Yeah.
As more sediment piles on top, the weight squeezes the lower layers. This forces the grains closer together and squeezes out much of the water that was trapped in the pore spaces between grains. It's especially effective with fine-grained sediments like clays and muds. They can lose up to 40% of their volume just through compaction.
Okay, so compaction reduces space. What does cementation do?
Cementation is really the gluing process. Water circulating through the pore spaces, even after compaction, carries dissolved minerals like calcite, silica, or iron oxides. These minerals precipitate out of the water onto the surfaces of the sediment grains, gradually filling up the remaining pore spaces and binding the grains together into a solid rock. This is what really gives the rock its hardness.
So compaction squeezes, cementation glues, got it. How does all this affect how we classify the rocks in the end? We talked about detrital, chemical, organic.
Right, that's the primary classification based on origin.
Yeah.
Within detrital, we use particle size, shale, sandstone, conglomerate. Within chemical, we use mineral composition, limestone calcite, dolostone dolomite, chert quartz, evaporates heli to gypsum. And then we also talk about texture. Most sedimentary rocks have one of two main textures, which clastic texture is what you see in all detrital rocks, and some chemical ones like coquina or oolitic limestone. Clastic just means it's made of discrete fragments or particles, clasts, that are cemented together. You could often see the individual grains. The other is non-clastic, or sometimes called crystalline texture. Here, the minerals form an interlocking mosaic of crystals. This is common in evaporites like rock salt, or some limestones and cherts where crystals grew in place. It might look a bit like an igneous rock texture, but the minerals involved are usually very different.
Okay, so if these rocks are Earth's historians, how do geologists actually read the stories? What are the clues they look for? You mentioned environments.
Yes, this is where we apply that key geological principle. The present is the key to the past. We study environments where sediments are accumulating today, rivers, deserts, beaches, reefs, deep oceans, and see what kinds of sediments and structures are forming there. Then when we find ancient sedimentary rocks with similar features, we can infer they formed in a similar environment long ago. We group these environments broadly into continental, on land, marine, in the sea, and transitional, at the shoreline.
Can you give us a quick picture of each? What kind of rocks or features might we find?
Sure, continental environments. Think rivers depositing sand and gravel on floodplains or in channels, maybe forming big alluvial fans where they exit mountains. Glaciers leave behind jumbled mixtures of all sizes called till. Wind piles up well-sorted sand into dunes. Lakes collect fine mud or maybe evaporates if they dry out.
Okay, land-based stuff. What about the ocean?
Marine environments vary a lot with depth. Shallow marine environments on the continental shelf get sand and mud washed in from land, but also lots of carbonate production reefs, limestone muds. Deep marine environments way offshore mostly get very fine clay slowly settling, except when those turbidity currents roar down, depositing layers of sand and silt called turbidites, often showing graded bedding.
Graded bedding? What's that?
That's where a single layer shows a decrease in particle size from bottom to top. Coarse stuff settles out first from the turbulent flow, then progressively finer stuff. It's a classic sign of a turbidity current deposit.
In transitional, the coastlines.
Transitional environments are where land meets sea. Think sandy beaches, muddy tidal flats, exposed at low tide, covered at high tide, sandy barrier islands protecting quiet lagoons, and river deltas building out into the sea, depositing huge amounts of sediment. Each leaves a characteristic mark.
So if I walk along a cliff face showing layers of rock, I might see evidence of different environments stacked on top of each other as conditions changed over time.
Exactly. And even if you trace a single layer horizontally, it might change character. That's what we call sedimentary facies.
Facies. Okay, what does that mean?
It means that different types of sediment were being deposited in adjacent environments at the same time. Imagine moving offshore from a beach. You might go from beach sand, sandstone facies, to nearshore mud, shale facies, to maybe a reef further out, limestone facies, all forming simultaneously, just in different places, reflecting different conditions.
That makes sense. So environments are key. What about specific patterns or structures within the rock layers themselves? What do those tell us?
Those sedimentary structures are incredibly informative. They form during or shortly after deposition, before lithification really kicks in. The most basic feature is strata, or beds, just the layers themselves. Each layer represents a period of deposition, and the surface separating layers, the bedding plane, marks a pause or change in deposition.
Right, layers. What else?
Cross-bedding. This is really cool. You see layers within a main bed that are inclined at an angle. This forms as sand blows over a dune, or washes over ripples or sandbars in a river or delta. The tilted layers point in the direction the current was flowing. It's like a fossil compass needle.
So you can tell ancient wind or water direction. Wow. What else?
We already mentioned graded beds from turbidity currents. Then there are ripple marks. Just like you see on a sandy beach or stream today, these can get preserved in rock. Asymmetrical ripple marks, with one side steeper than the other, tell you the current flowed in one direction, like a river or wind. Symmetrical ripple marks, more rounded and wave-like, form from the back-and-forth swash of waves in shallow water near a shore.
And mud cracks, like a dried-up puddle.
Exactly. Mud cracks tell you the sediment was exposed to the air and dried up periodically. Very common in tidal flats or desert lake margins. They indicate alternating wet and dry conditions.
And of course, fossils. They're structures, too, in a way.
Absolutely fundamental. Fossils tell us about the life that existed, which helps interpret the environment, and they're absolutely critical for determining the age of the rocks and correlating layers across different regions.
Okay, this is amazing. We've gone from weathering to deposition to rock types and structures. Let's zoom out one last time and connect this to the bigger picture. The carbon cycle. How do sedimentary rocks fit in? That seems critical for climate and life.
It really is. Carbon is constantly cycling between the atmosphere as CO2, the biosphere in living things, the hydrosphere dissolved in water, and the geosphere in rocks and fossil fuels. Sedimentary rocks are a huge part of the geosphere reservoir for carbon.
So how does carbon get locked up in these rocks?
Well, two main ways we've already touched on. First, through fossil fuels. Plants take CO2 out of the atmosphere via photosynthesis. If those plants die and get buried quickly in low-oxygen environments like swamps, their organic matter doesn't fully decay. Over millions of years, it transforms into coal, or can contribute to oil and gas formation. That's atmospheric carbon getting locked away in organic sedimentary deposits.
And burning those fuels releases it back, right?
Precisely. That's the connection to modern climate change. We're rapidly releasing carbon that took millions of years to store.
What's the other main way carbon gets stored?
Through limestone. Remember how CO2 dissolves in water to make weak carbonic acid? That acid helps weather rocks, releasing calcium and bicarbonate ions into rivers and eventually the ocean. Marine organisms then use that calcium and bicarbonate to build their calcite shells and skeletons. When they die, these accumulate on the seafloor, eventually forming limestone. This process locks up enormous amounts of carbon in chemical sedimentary rock. In fact, limestone is Earth's largest carbon reservoir by far.
So weathering rocks actually consumes atmospheric CO2 indirectly, and forming limestone locks it away.
That's the essence of it, yes. And conversely, when limestone itself gets weathered or metamorphosed, that carbon can be released back into the atmosphere as CO2. It's a long-term cycle, but sedimentary processes are absolutely central to regulating Earth's carbon balance and climate over geologic time.
What an incredible journey. From tiny grains to global cycles, sedimentary rocks really are telling complex stories. We've seen how they form, the clues in their grains and structures, how they record ancient life and environments.
That's right. Shale, sandstone, limestone, coal. Each one is like a chapter in Earth's autobiography. They hold vital clues about past climates where we find essential resources and the dynamic processes that continue to shape our planet.
Yeah, it goes way beyond just textbook geology. Understanding these rocks helps us deal with natural hazards, manage energy and water, and grasp things like the carbon cycle. It's fundamental.
And it makes you think, doesn't it? Given how sensitive sediment deposition is to things like sea level, rainfall patterns, temperature, how might our current period of rapid climate change influence the types of sedimentary rocks forming now? What stories will the rocks of the Anthropocene tell geologists millions of years in the future?
That is definitely something to mull over. A fascinating thought. Well, thank you for guiding us through this deep dive into sedimentary rocks. We hope all of you listening feel a bit more informed, maybe a lot more curious about the ground you walk on. Until next time, keep exploring.